Hello, ladies and gentlemen. Yes, good morning. It's Friday morning of a very action-packed, exciting and innovating week, so I imagine many of us are running on fumes, caffeine, cigarettes, and memes right about now. But let's dive into this. HONK, what is HONK? What I want to do this morning is discuss how to construct an efficient, privacy preserving SNARK using a lot of the modern tools and techniques that have come out over the last couple of years. So to take a step back, back in like the bad old days of the 2016, 2017, existing SNARK constructions were rather monolithic in that you had a way of converting a program into constraints, improving it, but there weren't any clean abstraction layers that one could compose these types of proving systems out of. Everything was very monolithic. Things have now changed a lot, where we've managed to refine the art of building proving systems into ones where we have these relatively distinct layers that we can compose together that allow a certain amount of modularity and flexibility. This has enabled the construction of very efficient proving systems, but also exploded the level of complexity one can engage in, and it makes the trade-off space very complex in terms of what do you value? Do you value raw prover speed? Are you resource constrained? Do you care about proof size? Do you care about recursion costs? Blah, 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 blah. So I'm going to try and break some of this stuff down. So at the start, we have our circuit arithmetization. That's where you have some high-level imperative computer program and you want to convert it into a representation that can be efficiently proved. So rank 1 constraint systems are a way of doing this. There's the Plonkish style system, there's customizable constraint systems, and arithmetic intermediate representation. So all of these. What they're doing is they're taking a program and they're converting it into polynomial algebra. Because we can prove algebraic statements, we cannot prove imperative statements like for loops. Once you have your algebra, that doesn't really help you that much because, okay, well, now you have some big complicated algebraic statement over, high degree, million degree polynomials. What do you do with that? Well, you need to prove it. That's where the polynomial interactive oracle proof comes in, where it's a protocol between a prover and a verifier, where the prover is basically claiming, I've got some polynomial relations I want to prove, and the verifier is going, all right, buddy. And it converts the checks over polynomials into checks over points. And it does this probabilistically. So the idea is, because nothing comes for free, the idea is that if the relation over points satisfies, then with overwhelming probability, the relation over polynomial satisfies, and therefore the program is satisfied. And if you have a polynomial interactive oracle proof, you need a polynomial commitment scheme. The idea is that at the start of the solve, the prover is going to commit to the polynomials. A commitment is ideally a succinct representation of your input data. So if I have polynomials with tens of millions of terms in them, then I can represent those polynomials using a very small, ideally constant size amounts of information. And then later on, the verifier can send the prover some random challenge that represents an evaluation point, and the prover can supply the evaluations of the polynomials and prove they're correct. So canonically, these are the three kind of layers that one builds SNARKs out of. 2023 has complicated things slightly with the idea of a concept of a folding scheme. So folding schemes are ways of, I see it as a way of doing recursion with fewer steps. But let's say you have a scenario where you need to verify a SNARK circuit within another SNARK circuit. So you've got circuit A, circuit B. You want to verify circuit B in circuit A. Like this is called recursion, even though technically it's not really a recursive structure in the ways that it's being used. And this has been a very thorny, difficult issue for many, many years. I've probably spent about, 2 man-years personally just trying to deal with this issue. Folding schemes are a fantastic solution where instead of verifying proofs, you kind of cheat, and instead you construct random linear combinations of the instances that define your circuit. It's basically taking the witness commitments and creating random linear combinations of those. That produces error terms, and folding schemes have very nice interactive protocols that allow for those error terms to be proved to be correct. So yeah, those are the abstraction layers that we're working with. So what the hell is HONK? So HONK is Aztec's new all singing, all dancing proving system that we are using to power the Aztec network. And it is a synthesis of a lot of different techniques, but it largely inherits from hyperplonk, which is a protocol which reformalized the plonkish circuit arithmetization, but to use the sum check protocol instead of quotient testing. And I'm going to go into that in a bit. If the click, yeah. So before going into the proving system, I need to go into what Aztec is, because there's if somebody in this conference comes to you and says, I have the best proving system, it's simply better than all the rest, and here's how it works, they're not being honest with you, because really what's happening is that we have a very complicated trade-off space where different applications are sitting at different nodes where we value different things, and we are tailoring our proving systems for those needs. And so Aztec has specific needs because of the nature of what we do. And what we do is private, programmable smart contracts, and the way we do that is we break down a smart contract into functions where each function is its own SNARK circuit. Why do you do that? Because we want composability. If I write a contract and Alice writes a contract and Bob writes a contract, I want my contract to be able to call Alice's contract and Bob's contract, which means you're now composing different algorithms that have been written by different people in a single transaction. How do we do that? Recursion, or folding, where you have some higher level SNARK circuit that will recursively validate or fold instances from individual function circuits, and that ends up defining a transaction. So what does that mean for the proving system that we need? Well, we're going to use the, hang on. Okay, here, I'm going to get these slides are slightly out of order. So, because Aztec's privacy preserving, we need our proofs to be constructed client side. That means so that secrets aren't leaked. And that means that we have very severe computational resource restrictions. We want our proofs to be constructed ideally in phones. If a user is coming to a DApp through a web browser, that means the proof needs to be constructed in the web browser. That means that we need to be able to construct our proofs in WASM. It means that the prover algorithm needs to be efficient enough that that Safari or Chrome doesn't kill the browser tab, which means we have about 1 gigabyte of RAM, which isn't very much. Like ZK AVMs usually use something like 0.5 terabyte. And we're very sensitive to proof sizes, oddly enough, because a user transaction contains a proof, which means if I want to send a transaction to the Aztec network, that transaction needs to go into a peer-to-peer mempool, so that a sequencer can then pull transactions out of the mempool and include them in the block. And if we want Aztec nodes to be run by commodity hardware, that means that the amount of information going through that peer-to-peer pool has to be less than the bandwidth limits of a modern broadband internet connection. So if you have a 100 kilobyte proof and you want to target 1,000 TPS, that's 100 megabytes a second of data minimum. That's very painful. So we're very sensitive to final proof size. And we are exceptionally sensitive to the recursion cost, because we have this composable system where you have contracts calling contracts calling contracts, and each time that's happening, we are recursing to assemble these function calls together. We're estimating we want to do between 8 and 32 recursive verifications or foldings within a single user transaction. That must be proved client-side. So this is a very extreme requirement that cannot be met by any existing folding or recursion scheme. Ideally, we want to get a proof of recursion or folding in about 10 milliseconds in a web browser. Oof. And these are all targets, they're not benchmarks. This is all still work under construction. We've basically built all the core components, but we're stitching them together, which will be done by the end of this year. But then we will need to spend a lot of time optimizing to get down to these targets. So what are the abstraction layers that we're using to build HONK? we're using the ultra-Plonk circuit arithmetization. What does that mean? It means that it's basically Plonk with a few custom gates and lookup table support. We have extremely efficient range checks by modifying our permutation argument, and we are using the log derivative techniques from Ulrich to do our lookup arguments. So yeah, we've goodbye lookup, unfortunately. One of the big changes from Plonk to Honk is we are not constructing a quotient polynomial and checking that our polynomial arithmetic vanishes over a subgroup. We are using the sum check protocol, so it's a much older construction from the 1990s, which is much more efficient, but up until recently there have been severe problems with getting it to work with Plonkish type systems that have recently been solved. So sum checks, for them to be efficient, you need to work over multilinear polynomials. So instead of having a univariate polynomial, where the evaluation of the polynomial at multiple roots of unity produces like values in your vector, as basically using polynomials as vector commitments. We use multilinear polynomials as vector commitments. So now we have if you have a size n vector, you have a log n dimensional Boolean hypercube where each vertex of that cube represents an element of your vector. The reason why sum checks are pretty OP here is that they're fully linear time. This means that our proving system is fully linear time because we're using linear time polynomial commitment schemes. And this is wonderful for memory consumption because because we're not using fast Fourier transforms, it means that if you have witness values in your circuit that are small, say Booleans, they stay small when you're constructing your proof. If you apply a fast Fourier transform to a witness, a vector, a polynomial of Booleans, then over your extended domain that you're applying FFT to, every element becomes a full finite field element, which means that you've expanded a one bit of information to 32 bytes. That doesn't happen in the sum check protocol, and that's a huge reason why we're using it, because it means it's much more memory efficient. We're estimating we're going to use 5 times less memory than ultra-Plonk and Turbo-Plonk, which was the techniques we used in Devconnect. The reason why sum checks have been hard to get working is because multilinear polynomials require multilinear polynomial commitment schemes. Previously, traditionally, those kind of suck. They're very expensive, and there was no efficient way of getting this kind of concept of a shift that you need in Plonk. So the idea with Plonk is you have a commitment, you have these, you can consider like instead of thinking about gates, where you have wires going to gates, imagine a table where you have 3 columns for the wires in Plonk, and each row is a constraint. Let's call that an execution trace. So for Plonk, we need to be able to shift those columns. So the idea is that you can basically perform a right shift on all the column values. That's easy to do with univariate polynomials. It's difficult to do with multilinear polynomials because there's no uniform transformation you can apply to a multi-dimensional Boolean hypercube to get that kind of shift. Zeromorph solves this. It's a multilinear polynomial commitment scheme that my colleagues Patrick and Toro produced earlier this year. It's extremely powerful, very efficient, and basically it enables relatively trivial linear isomorphisms between multilinear and univariate polynomials to be proven succinctly. And then finally, a long slide I know, we're using the proto-galaxy folding scheme. This is very important for Aztec because there are 2 flavors of folding schemes. So you have the nova, hypernova folding schemes, and you have protostar, proto-galaxy folding schemes. And the star galaxy constellation enables multiple different circuits to be folded into a single accumulator. That's important for Aztec because every function in a smart contract is a unique circuit, which means, well, we have every circuit is distinct. And then finally, we're using Goblin Plonk. So this is the most degenerate components of our tech proving stack. We call it a folding accelerator. It basically takes there are some computationally very expensive components of folding schemes. Specifically, you need to do this it's called Ron-field arithmetic over basically you have this elliptic curve arithmetic that one needs to do that's over a field that's not native to your SNARK. It's very horrible. Goblin Plonk is a solution that will transform your expensive, not wrong field curve operations into curve operations over a native field. So, bonk. Oof, yes, okay, so here's some weird asymptotics. I just need to take a slight drink. You know, normally we do questions at the end, but I think if we could maybe modify the format, it might be useful to have some questions halfway through. Would that be possible? I don't know if people are standing ready with microphones. Does anyone have any questions? Oh, yes. Gentleman at the back. You might have to yell. So the question was, why not use Nova folding? It's a good question. It's because with Nova is a very efficient scheme to fold multiple instances of the same circuit over and over and over again. So for example, if I want to do like a gigabyte of Keccak hashing, I can create a single circuit that does a megabyte, and I can just use Nova to repeatedly fold that circuit over and over again. We don't use it because we need to fold different circuits. The idea is, in Aztec, we have this concept of a kernel circuit, inherited very much from the Zexi, where the paper, where the kernel circuit is going to be, okay, well, actually, let me just slightly talk about the architecture. So we have a concept of a function call stack in Aztec. The idea is your kernel circuit has an input function call stack and an output function call stack. What the kernel circuit will do is it'll pop a function of the input call stack and verify a proof associated with that function call. And then depending on what on the public inputs of that proof, the kernel circuit may push additional function calls onto the output function call stack. If that will happen if the function is calling other functions. So this is a highly recursive structure. The idea is that you recursively construct kernel circuit proofs until the output function call stack is empty. But each function call is a SNARK circuit that is where we've taken a noir program that defines the function and we've compiled it into a HONK circuit with a specific verification key. And it means that all of these function circuits are distinct from one another. They're not and Nova can only fold the same circuit over and over and over again. We need to take completely arbitrary circuits and fold those into a single kind of accumulator object. Nova can't do this, but Protostar and Protogalaxy can. Although it's not explicitly mentioned in the paper, it's a relatively trivial modification. Does that answer? Yep, all good. So do you have a follow-up? Cool. No, it's all good. Maybe one other question before we move on? No. Is everyone too sleepy? It's been a long week. Yeah. Okay, well, we can move on. So, you know, normally whenever a new proving system comes out, there's going to be a paper on ePrint, and that paper is going to contain a table, and that table is going to be comparing the proof system with other proof systems that are similar. There'll be charts, there'll be diagrams. Most of these benchmarks are somewhat juiced, I would say, overfitted. So I'm a little bit hesitant to provide hard numbers or asymptotics because there's lots of variability here. But I can give some general descriptions of the performance. So the prover costs, it's going to be linear in the number of constraints. So n is the number of constraints. D is the algebraic degree of your constraints. What do I mean by that? So if you have a Planck gate which multiplies five columns together, that's a degree 5 constraint. If it just if it's multiplying 2 values together, it's a degree 2 constraint. And so the complexity scales with the square of the degree, that's just intrinsic to some checks. It's a little bit painful, but such is life. As long as D is small, it's not a big deal. And we have a linear number of elliptic curve scalar multiplications. There is a modification that we can do here, which we're very excited about, but we're not going to implement yet because it's high complexity. But it's possible to take Planckish systems, and when you're committing to them over elliptic curves, the elliptic curve commitment cost, it's not proportional to the number of wires in your circuit is proportional to the number of unique wire values in your circuit, which is generally significantly smaller. But that's an optimization. And the memory consumption is linear in the number of constraints and with relatively small constants. The cost of the recursive verifier is fixed, basically. It's just a single straight fixed cost, and the constants are, whilst they're large, they're a lot smaller than they used to be in the past. So effectively, why would you want to use HONK? Why would you want to use HONK? If you're building a ZK EVM, don't use HONK. The big downside of this type of proving system is that it relies on elliptic curves because we need to use folding schemes, and elliptic curves require operations over large finite fields. Whereas if you want to use a more Fry-based construction or a SNARK-like construction, you can use much smaller prime fields, say 64-bit prime fields instead of 256-bit prime fields. And the cost of a prime field operation scales with roughly with the square of the number of bits in it. So basically the trade-off here is if you are doing a large computation, if you're proving large computations, and you have a lot of resources to make that proof, so you have some big central compute cluster, generally short field, Fry-based or SNARK-based constructions will be faster. The reason why we're using elliptic curves is because the recursion cost is outrageously low. And for us, that is the dominant requirement. That's combined with memory consumption. Because if you are memory constrained, then you want to be able to create a heuristic where you can break down a complicated program into smaller computational blocks that you can then compose recursively. And that means that you need the cost of the recursion primitive to be extremely small, which for us it is. So I've been talking about the high level of HONK, and to be honest, that was the main focus of my talk. So this entire presentation goes into the nitty-gritty details to quite a large degree, but given it's a Friday morning and there was only 30 minutes, I'm not going to go through it all, but I can blitz through some of the high level of the details. So the multilinear sumcheck protocol. I think there's been a very big shift over this year where sumchecks have become kind of the in vogue fashion amongst the Web3 cryptography community, but I'm not sure how much that's percolated outside of small-scale discussions. But let's say you have some input polynomials. So yes, sorry, I'm going to subject you all to a little bit of maths. So trigger warning, the X's are to your left and right. So you have a bunch of input polynomials and some polynomial identities. So some expression involving these polynomials where we want, where the idea is that we want, if you evaluate our multilinear polynomials over every single combination of zeros and ones for each variable, and we apply the identity expression for those evaluations, and then we sum over the potential set of evaluation points, the identity equals 0. That's what a sumcheck protocol will check. And if you want to convert that into a protocol that will check satisfiability of circuits, one needs to do some minor modifications to it, because what this is effectively doing is it's saying, if the identity is your gate equations, and the evaluations of your multilinear polynomials at a specific set of zeros and ones represents a row of your circuit, this is saying that the sum of the row expressions equals 0. We don't want that, because we want each row expression to independently equal 0. So okay, this is the whole protocol, but I do not have time to go through this, sorry. Well, if anyone wants to take a picture, I'll leave it up for a few seconds. But this is kind of like a summary of the interactive protocol that one will use to verify a sumcheck. It has a multiple round structure. Equivalent to the number of rounds is the dimensionality of your hypercube, which is a fancy way of saying it's the log of your circuit size. Where for each round, the prover is going to be creating, it's called like a univariate reduction, I think, of your multilinear expression. The idea is that we are considering each variable in our multilinear polynomials individually in turn. And after each round, we're then substituting that variable with randomness at a very high level. And the eventual outcome of this is that the protocol reduces a claim over polynomials into a claim over points. The idea is that the verifier needs to evaluate the the sum check expression, so like the circuit, Plonker's circuit arithmetic expression, over a set of random points that the polynomials must be evaluated at using a polynomial commitment scheme. Which leads me on to the commitment scheme. So zeromorph. What is zeromorph? So it's a member of a family, I would say, of commitment schemes, which basically use transformation layers to transform multilinear polynomials to univariate polynomials. I believe Gemini, there's a protocol in the Gemini paper that was the first. Zeromorph was the second. And what zeromorph does is my colleague noticed that basically there's just a simple linear isomorphism between any multilinear polynomial and any univariate polynomial, and a univariate polynomial equivalent. And because it's linear, you can construct a relatively efficient protocol with a constant number of rounds that will check this linear relation. And what it basically enables one to do is commit to a univariate polynomial, but kind of pretend it's a multilinear polynomial. And then when it comes to evaluating the multilinear polynomial at a point, the prove and the verify run an interactive protocol to transform that into an evaluation of a univariate polynomial at a single point. It's very efficient for multilinear schemes. So if you have a degree n polynomial, you have 2.5 n multiscalar multiplications to perform, which is only slightly worse than the best univariate commitment scheme, KCG. And the proof size and the verifier time are both log n, which is slightly annoying, but can be gotten around. And it requires 3 pairings, which is nice, because a lot of other schemes require a logarithmic number. Burp. And okay, this is way too much information. There is a paper in ePrint called Zeromorph. If you want to choose from glass, I'd highly recommend reading it. It's fantastically written, and I can say that because I wasn't involved in writing it, so I'm not shilling myself. And then folding schemes. So the idea with folding schemes is you have multiple instances of a SNARK relation. So what's an instance? An instance is basically if you consider the witness statement for a SNARK relation and the input string, so the public information that encodes the SNARK circuit. So for Plonk, that would be the pre-computer selective polynomials. Those two combined form an instance. And even multiple instances, then ProtoGalaxy has a very nice way of folding those into a single instance, called a randomized instance, because, well, there is an error term that propagates, but it can be factored out. Folding schemes slightly change the paradigm, because instead of the paradigm where you have an interactive protocol between a prover and a verifier that you then make non-interactive using the Fiat-Shamir heuristic, you really now have 3 actors. You have the folding prover, which will be folding instances into an accumulator. You have the folding verifier that will be validating that this folding step has been done correctly. But then you have this concept of a decider, so a decider prover and a decider verifier, which is another interactive protocol that will validate that the accumulated folded instance is correct. And that's the expensive part of folding schemes. So I've noticed we have 2 minutes to go. And I think yeah, I think we should probably stop here, because this is going to segue then into the detailed specifics of what the HONK and ultra-Plonk relations are, which would be another 30 minutes of time. But yes, thanks for coming to my TED Talk. Thanks for listening to me talk about this stuff. But this is, yeah, if you want to create very fast client-side proving systems, well, I'm not going to say I have the solution, but I will tell you that this HONK is our solution for solving this problem. Thank you very much.